Hi everybody, welcome back to the Feynman technique. Today we're going to be evaluating an integral similar to the one I did in my last video. You can see this is the arctangent of the integral of the arctangent function evaluated at another trigonometric function squared. In this case, it's secant squared x. I believe the last one it was sine squared x. Um, so let's just get started. So my first move in solving this integral is just going to be to rewrite that secant squared x as 1 over cosine squared x. And it's going to become clear why I did that here shortly. You wouldn't think that would be any better, but with the technique that I'm going to use, it is a little bit better. So the next thing, and this might seem like an odd next step, but I just want to state something or show something. If we have the natural log of any complex number a plus bi, where a and b are real numbers, that's going to be equal to the natural log of, well, a plus bi, if we represent that in complex exponential form or polar form, it's going to be the magnitude, in other words, the distance from the origin, which using the Pythagorean theorem would just be the square root of a squared plus b squared, times e to the I multiplied by the angle that this point makes. And that would be the arctangent of b over a. So we have this, and then using the properties of logarithms, we can split that up into two separate expressions, one being the 1/2 the natural log of a squared plus b squared, and the other being the natural log of e to the I arctangent b over a. Of course, the e and the natural log will cancel out, leaving you with this. So, in other words, the imaginary part of the natural log of a plus bi is just the arctangent of b over a. And you'll see we have that form right here where our b is 1 and our a is cosine squared x. So that's why I did that. All right, so next we can just rewrite I as the imaginary part of the integral from 0 to pi over 2 of the natural log of I, which is our b part. Well, our b would be 1 because this is technically 1I. So we can rewrite it as the imaginary part of the integral from 0 to pi over 2 of natural log of I plus cosine squared x. Well, why did I do that? Because I've already developed formulas on this channel of this form. If you have some function of t that's equal to the integral from 0 to pi over 2 of the natural log of t plus cosine squared x dx, I've solved similar functions like that on this channel before. You can see that we just have an I replacing our T. So next, we can say that our original integral, big I, is the imaginary part of our function f of t evaluated at I. And we'll also state that f of 0 is just going to be the integral from 0 to pi over 2 of natural log of 0 plus cosine squared x. Of course, that's just cosine squared x. And with the properties of logarithms, you can bring that 2 outside the entire integral. And I've solved this integral right here on this channel a few times before using King's property or King's rule. And that integral equals negative pi natural log 2 over 2. So 2 times it is just going to be negative pi natural log 2. So we have this right now. F of 0 is negative pi natural log 2, and the imaginary part of our function f of t evaluated at the imaginary unit is our original integral I. Okay. So now we're going to use the Leibniz rule for differentiation under the integral sign to differentiate our f of t with respect to t. And we can do that just by taking the partial with respect to t of the integrand, which is going to give us this. And this can actually be evaluated with traditional integration techniques. I'm not going to show the work there. but that will evaluate to pi over 2 times the square root of t times t plus 1. And you can write that different ways, but this is just how I chose to write it. So our f of t, since this is f prime of t, and apologies for the notation, I always express it f1 of t when I am graphing these things in Desmos because it doesn't like graphing f prime of t. So just know that this is just f prime of t. I forgot to switch it back before I made the video. But our f of t is just going to be the antiderivative of f prime of t. So we antidifferentiate f prime of t, which is this. And again, not going to show the work, but you can use traditional techniques to show that it is equal to this, plus a constant of integration. And next, we will use the fact that we know that f of 0 is negative pi natural log 2 to show that c is negative pi natural log 2. Therefore, our function of t expressed in just normal terms, not as an integral, is just equal to this. All right. So, what did we say before? I is the imaginary part of this thing evaluated at I. And you'll see this part would drop out if we're taking the imaginary part. So I is just the imaginary part of pi times the natural log of the square root of I plus 1 plus the square root of I. Now, that's not super easy to take the imaginary part of, so I'm going to show some of the work here. You can go ahead and take a look. You can go ahead and take a look at this. One step follows from the last. I don't want to waste my breath and say everything that's on the board there. But once we get to this point, we know that I is equal to pi times the imaginary part of this thing. And you'll see we now have the natural log of some a plus I b. And we can use that same thing that we did before this. We can use this identity, imaginary part of natural log of some a, which is this part, plus bi, which is this part. Here's our b, is just going to be equal to the arctangent of our b part over our a part. So our original integral is just pi times the arctangent of this part right here over this part right here. And I wrote that right there. All right. So now we want to, we're technically done. I mean, this is a legit answer to that, but I mean, it's not nice to leave it like that, although it is correct and it is expressed in terms of elementary functions. So I could have technically left it like that, but we can do a lot better. We know that cosine pi over 4 and sine pi over 4 are both equal to square root of 2 over 2. Lesser known is the fact that cosine pi over 8 is equal to the square root of 2 plus the square root of 2 over 2, and that sine pi over 8 is equal to square root of 2 minus square root of 2 over 2. Easy enough to show with the double angle or half angle formulas for sine and cosine that is true. But so we're just going to substitute those values in, and what we end up with is this, and that looks even worse, but don't worry, we can even do better than that. Now, I'm not going to show the algebra in this, but if you do a lot of algebra, you can actually show that this expression right here is just the square root of the square root of 2 minus 1. So that is how we're going to leave it. So to finish things off, we now know that the integral from 0 to pi over 2 of the arctangent of secant squared x dx is pi times the arctangent of the square root of square root of 2 minus 1. All right, guys, hope you enjoyed that. We'll see you next time.